Now that we've learned how to do the one-way ANOVA and the repeated measures ANOVA, let's learn how to do factorial ANOVAs. Factorial ANOVAs are going to have multiple independent variables, and depending on whether they're between subjects, within subjects, or a mixture of both of the independent variables, will determine which factorial ANOVA you'll actually do. So first, we're going to go over the independent factorial ANOVA. This is like the one-way independent ANOVA in that it's just multiple between subjects variables. People are randomly assigned into technically 4 or more conditions, and it's like one independent variable and another independent variable. Let's use this example from the LSJ dataset as an example, the RTFM dataset. I'm not really sure why it stands for, like why it has that name, but we have two independent variables, whether or not they attended lectures and whether or not the student actually read the textbook. So 1, they did it. 0, they didn't. Let's see if there's more information in here. Nope, that's it. We could rename it. So I could change this to attended lectures and did not attend lectures. So we can do that type of stuff to make it a little bit more clear what we're comparing. I can also just Control-Z and undo that. So this is a nominal variable. Good. Reading, nominal, could do the same thing here. 1, they did read. 0, they did not read. And then we're looking at how both of those factors, right, two-way ANOVA, affect their grade. And so we've got the distribution of grades in this class. And then what do you think this is? This is just ever increasing by 1. So this is probably actually an ID variable. So we could change that and change this to ID. Okay, so we've got our data. We've looked at it. We're looking to see how both attend and read affect their grade. So we can't do just one at a time. We want to look at the combination of them too. So let's run it. We're going to go to ANOVA and we're going to go to ANOVA because we only have between subjects variables. So we'll click on that. Our dependent variable is our continuous variable. Actually, I should probably specify that this is continuous, right? This is continuous. There we go. So let's go back to our ANOVA. Note that I can just click into it, right? Hopefully we figured that out by now, but sorry if you hadn't and you are redoing things a lot. Our dependent variable is our continuous variable, our outcome variable, the grade. So we're going to move that over here. We're going to just click both of those, shift and hold, and move them over to our fixed factors. You'll notice it automatically adds this interaction effect. So we'll talk about that in a second. So let's make sure we do everything. Let's see, I think overall model test, do I like that? Actually, I don't really care for that. We want omega squared. I like the omega. It's a little less biased of an estimate. Our model is built this way, and if I didn't want that interaction, I could take it out. But I do want it, so I'm going to move it back in, and then we can put it in. If we had a lot of variables, then we could have all of the main effects, all the two-way interactions, three-way, four-way, so on. So if you have more complicated models, which I don't really recommend, like a 5-way interaction is probably not very defensible. 4-way, probably not so much either. 3 is kind of pushing it. A 2-way interaction is okay. Okay, so we're done with model, assumption checks, homogeneity, normality, QQ. We'll do all this. But remember, when we're doing normality and stuff, we should also check the skew and kurtosis. I'm just going to skip that for today. Contrasts, we'd probably assume that, well, actually, the fun thing about this is interesting. We only have 2 groups. If it's significant, so for example, attend is significant, then one group is higher than the other. That's the only option, right? So actually, and watch what happens when I do this. It's going to say, I think it's going to tell me, oh, it gives it to me, but there's no point, right? Because this is actually the same p-value as this. And watch this, the t-test, 4.27, let's get that calculator up, 4.27 squared, 18 point, it's, rounding error, but actually, yeah, because if we change this, it's probably 4.265. Let's just do that squared. Oh, that's still not working. Oh, because it's probably up 4.273, let's say, and then squared. 8.25. Yeah. So it's because of rounding error. It's the same thing. So you actually don't even need to do post hoc tests if there's only 2 levels to that particular independent variable. So that's the cool thing. If you have 2, if you have 3 or more, then you need to do those post hocs. So we'll get rid of that because we really don't need it. I suppose you could get it so you could get your Cohen's d, but you've got your measure of effect size here as your omega. Okay, assumption check, contrast, post hoc, we can ignore all of that because we only have 2 groups per IV. I'm going to get the, I like to get the plot in there. Because I need to move it over. And we're going to move a new term, see if this is how it works. Oh yeah, so it's putting them both separately. I actually don't want that. I want, let's get rid of, start over. I think I can, yep, both in together. Because that's what I really want. There we go. So now I've got my interaction plot of the interaction between attendance. So this is attendance, did not attend, did attend. And the reading. This is did not read, and this is did read. So we see that overall, like I can just look at this and kind of interpret it a little bit. Those who did attend seem to have had a higher grade than those who did not attend. And those who did read have a higher grade than those who did not read. But because these lines are fairly parallel, I'm going to guess, and I may have looked at the p-value, but I didn't actually. I'm going to actually guess that the p-value for the interaction is not significant because it's kind of just parallel. There's no significant interaction between attendance and reading. I think. Let's find out. Hello. Yeah, there we go. So not significant there. Why is my F so crazy? That's weird. I don't know. I guess because it's just real big. It's doing that. Okay. So we've got all that. Save. We don't need the residuals. We'll learn about that when we get to regression. And if we wanted, we could get the tables as well to get the actual means of each of the 4 conditions. So that's these dots right here are those means. Excuse me. And then the standard errors are here. Actually, these are standard errors. There's our standard errors. If you wanted the confidence interval around their mean, then that would be this. So it defaults to that, but we can change it to standard errors. Okay, so we've got all the stuff. Now we can interpret. First, we need to look at our assumptions. So Levine's test, significant. We actually don't meet the assumption of homogeneity of variance. So probably should be doing a non-parametric thing or trying to clean this up. But we also, we have 8 data points. That's not very much. There's not much to work with. So we're just not going to worry about it right now. But reality, we should have a lot more data, particularly because we have a lot of error around the data. So like people in the food science, when you're testing food, I notice you have very small errors, and that's why you can have smaller data sets and smaller kind of repeats of data because your error is so much smaller. Let's look at normality. QQ looks great. Normality looks great. Awesome. We can proceed and do our analysis. So we go up to our ANOVA table. Let's read this. We're looking first at the effect of attendance, and we can scroll over. You can kind of skip this, right? You need the degrees of freedom to write up the results, but you can kind of skip the sum of squares and means of squares. It's just how we calculate the F test. There's math behind it. If you want to know the math, let me know, and I can put a little thing up that shows how we can actually calculate all this. With a sample of 8, this would probably be pretty straightforward to calculate and do manually. So we get an F test of 18.25. That's big enough that I'm like, oh, that's significant. And lo and behold, it is statistically significant. And our omega is about 0.26, so it's pretty like a small to moderate size. Reading is also statistically significant. And so there's a significant effect of both attendance and reading on grades individually, main effects. And this one's an even bigger effect. So reading seems to be more important than attending in affecting grades. but there's no significant interaction between attendance and reading on the p-value, and the omega is basically 0. And this is a perfect graph to include when we're putting it in our write-up. So we could include that. And then let's show how to write this up. So I'm going to go to the textbook. Notice that I'm just at the link. And notice how I have the post-hoc test, but really not that informative, because all we could do is just look at the graph and know that perfect. We know which group is better. So let's write this up. So hypothesis, knowing how attendance and reading affected students' grades. That's our basic research question. An independent factorial ANOVA showed that both attendance, let's do this side by side actually, that both attendance, and we do the F for that particular one, so F 1, 4, 1, residuals equals 18.25, P equals 0.013, omega squared equals 0.26. And reading affected students' grades. And go back, reading, we have 1, 4, 44.17, P equals 0.003, omega squared equals 0.64. And so that's the overall result, right? Because we have both of them. And then I also specified there was no significant interaction between attendance and reading. Okay, so that's this line. F equals, oh, that's wrong. Ooh, nice error. I'll have to fix that. F equals 0.23, P equals 0.660, omega squared equals negative 0.01. Cool. So now, once we've done the overall ANOVA, now we do those post hoc. And really, I suppose I don't really need the post hoc comparisons using Tukey's, because it's just, like I said, it's exactly equivalent. There's like no reason to do it, but whatever, we can do it anyways. Pastana did it, so we'll talk about how Pastana did it. Students who attended lectures, and we do the mean and standard error, had higher grades than students who did not, mean, standard error, and then I did the p-value and the d. You could also write it out fully with the t-test, so let's go back here. If we went to the post-hocs, we did both of these over with the Tukey's and Cohen's D. Now, notice how it wasn't there before. Oh, it was there. So we could write up with the t's test in there. So like t bracket 4 equals negative 4.27, comma, p equals, right? We could put all that in there. Yeah, either way. Another point, some people are asking about the difference between standard error and standard deviation. Is basically the same. The standard error has more information because it actually incorporates the sample size into its calculation. I'm going to show you something. Hopefully I have the equation correct in my head. Grade, let's see if this works. Perfect. Okay. So, we have our standard errors, but the standard errors are a pooled standard error, so it's not even quite right, because watch, if I do standard error of the mean, notice how they're all different, but it's the pooled standard error that gets us to 2.98. But I think let's see if I got this right. Oops. Divided by 8. 7? No, I can't quite remember how we calculate the standard error. There's an equation from standard error equation. I thought it was just the standard deviation divided by, but I was close, but divided by the square root of n. So that would be 10.61 divided by the square root of 8. Oh, it didn't like that. Okay, let's try that again. 10.61 divided by 8 square root. Here we go. 2.83. Still not quite right. Simple standard deviation over the square root of n. Oh, maybe because it's 2. Technically 2. Divide by 2 square root. 10.61 divided by 2 square root. 1.41. Still not quite getting it. I don't know why. Because, right, there's 2 right here. 10.61 should be 7.5. Am I still 10.61 divided by the square root of 2? I should be higher than this, so something's wrong. Let's see. Let's just do this. What's the square root of 2? Clear. 1.41. So 1.41. Yeah, there we go. 7.52. I don't know why. I don't know. I guess I don't know how to get that to work in the calculator. So, this is just calculated by the standard deviation divided by the square root of n. And so in this analysis, this is the pooled standard deviation divided by the square root of n. So that's why we're getting all the same standard error. But notice how the standard error is just a function. It's just a simple equation of the standard deviation over the square root of n. So you can do both. Some people also recommend that if you're going to do the standard deviation, that you also put the n in there. So you could put that either within, like here, m equals SD equals n equals, or you could just say they were completely like it was 2 people per condition, per the 4 conditions total. Either way, okay. So that students who attended lectures had higher grades than students who did not. Furthermore, students who read had higher grades than students who did not. So notice how I read that out loud and it made sense. Post hoc comparisons using Tukey's HSD showed that students who attended lectures had higher grades than students who did not. That reads very clearly grammatically. So take all the parentheses stuff out, and if you can read it and it makes sense, you've done a good job. It's a good check for yourself. Okay. And then we talked about interactions. Here's another version of the plot. Yep. So here's the interaction. So just like I said, parallel lines are showing me that there is no interaction. You can go to this website. So let's go ahead and go here. And it's going to show you how to interpret some interactions. So you can do it by a bar. You can view it as a bar graph or as a line chart. And you'll notice that there's a main effect of A, whatever the A is, but no effect of B because they're right next to each other. And there's no interaction because they're basically parallel. For this one, there's a main effect of B. B1 is higher than B2, but there's no effect of A because the average of those is the same. And there is no interaction. Again, they're basically parallel. You can look at it as a bar graph. This one, there's 2 main effects. Notice how it looks very similar to what we've got. Effect of A, effect of B, but there's no interaction. This one, no interaction, no main effects. Okay, here's our first one with interaction. There's an effect of A goes up. No effect of B because the average of B is actually the same. You can look at it this way because the average will be the same. Right? Average is still just here and here. Or I always have to transpose it. But there's a significant interaction because they're kind of crisscrossing basically. Or they're deviating like this. Here's another way to put it. Significant effect of B, no main effect of A because the average is going to be the same across A. And there's an effect of B, but and an interaction. Here's another way to look at it. And so on. So you've got that link to play with. And that is the Factorial ANOVA for an independent design, all between group independent variables. So add your comments, add any questions you have, and we'll go on to the repeated measures Factorial ANOVA.